So this is about formaldehyde from oxidation of methane. So methane is there. It is undergoing oxidation to get formaldehyde, as well as there is a side reaction that is leading to carbon dioxide and this water vapor generation. So there are two parallel reactions, and methane and oxygen are the feed to the reactor. The product gases leaving the reactor include methane. This product also has methane. Of course, it is also having oxygen and formaldehyde, carbon dioxide, and water vapor. So otherwise, these reactions are completely saying about the product formations. Okay. Now, what is given is 60 moles of methane is entering the reactor. The molar flow rates of methane, oxygen, and CO2 leaving are given. So we need to find the molar flow rate of oxygen entering the reactor. So how much of O2 has to enter? So as we know the moles of methane, we need to find moles of oxygen. Of course, we are also having some idea about moles of methane in the outlet and O2 in the outlet and CO2 in the outlet. So let us first directly go to the extent of reaction method. So extent of reaction, here we have two reactions. So first let us represent the process. So before coming to that, this is the reactor to which methane is entering and oxygen is also entering. We are given with the feed to the reactor. Methane and oxygen are the feed to the reactor. So methane is entering. The molar flow is given as 60 mole per second. N2 we need to calculate. Here the product, what are all possible? The product they say like when methane is there, O2, CH4, CO2, H2O. So these are all the product constituents. So here we can write this. Of course, let us take this methane as N1 and oxygen as N2. Then this methane and the product as N3. Then here N4, N5, N6, N7. Okay. For certain components, the molar flow are already available because there is a data says the molar flow of methane, O2, and CO2 in the leaving are 26, 2, and 4. There is methane, oxygen, and CO2 are available. Methane, oxygen, and CO2, the moles leaving are available. Okay, let us take this moles of CH4 as N3. This is N4, N5, N6, N7. Okay, N3, we can also write it as, this is a formula for writing this moles of a constituent given the molar flow in the initial moles and the stoichiometric coefficient and the extent of reaction. So let us try to write this for methane. So methane is there here. And what is the stoichiometric coefficient? There is 1. Of course, it is having a sign of -1. Minus, because stoichiometric coefficient is positive for the products and negative for the reactants. So here always this is -1 and this is actually -2. That we have to understand. So let us write for this CH4, which is always Ni we are going to write, which is nothing but N3 here. Ni naught is the initial amount of methane, which is nothing but the N1 actually. This is simply Ni naught equal to simply N1. Whereas this amount is already known to us, which is 60 mole per second. So 60. And what is this term for this CH4? So otherwise this is what it says, sigma nu I Ej. So nu ij, what is nu ij? Nu I of jth reaction. So what is the nu I for this CH4? This is -1 and -1, and it is E1, no? Because the extent of the reaction is E1. And for the another time, this is summation, right? So this is summation of nu I j, nu ij, Ej. So this is coming from the first reaction, and from the second reaction we have, for the second reaction also it is stoichiometric coefficient is -1. So -1 into E2, that is -1 into E2. So sorry, minus E2. So that is for the second. That is for the first reaction and second reaction. We are simply writing what is it? Nu I Ej. That is sorry, nu ij Ej. So what is nu ij Ej? This is -1 minus 1 into E1 or simply minus E1. And for the second reaction, it is again this is also minus 1, so minus E2. So this thing is simply minus E1 minus E2, and Ni naught is simply 60. So which is already given as 26 moles. Otherwise, N3 is equal to 26 moles, which is also as 60 minus E1 E2. This is from writing from the extent of reaction. And this N4 is that of oxygen. N4 is again, say is Ni equal to Ni naught plus this, no? So for the N4, we are having this initial moles, which is N2, otherwise this is nothing but N4 naught. N4 naught is nothing but N2. So that's why I'm writing as N2. And what is for this O2? For the first reaction, it is minus E1. For the second reaction, it is minus E2. Minus 2E2. Minus E1 minus 2E2. That is, the stoichiometric coefficient is minus 2. So that's why we have this O2 is N2 minus E1 minus 2E2, which is already given as 2 mole. And that of this formaldehyde, we take it as N5, and CO2, which is N6, which is given as 4. What is N6 or is CO2? CO2 is what is the stoichiometric coefficient of CO2, which is simply 1. And how to write this in terms of this nu I Ej? That is for the second reaction. So that's why this N6 is E2. You can also refer to, suppose if you feel it difficult to go through this material, I also uploaded in our I suppose sorry, I haven't uploaded. So okay, maybe I will in the coming classes at least I will upload prior, so that you can also go through these or you can go through front and back. So that will be very helpful. No? Sometimes you may not be in a position to follow this along with me. So otherwise you may want to refer why it is coming that way. So better I will upload these problems also in the coming classes, so that you will also come prepared. Okay, now in the flow, this N5 is simply E1. Why it is E1? Because only in the first reaction it is there, and again it is a positive with a coefficient of 1. And what is that of N6? N6 is CO2. CO2 is there in the second reaction, or this is simply E2. That's why it is written that way. And what is that of H2O? H2O is there in first reaction as well as there in the second reaction. So which is, of course, there is no initial, or is Ni for water is equal to Ni naught. Ni naught is 0. There is nothing in the feed. So always Ni naught plus sigma nu I j and what is it, Ej. So here it is E1, and this is plus 2E2 because 2 times. So that's why we have E1 plus E2. Okay, that is written. Now, what are all available? So at last we need to get the moles of O2. That is what is molar flow of O2. So we need to get O2 amount in the feed. Otherwise, we need to get N2. That's what we are going to solve for. Because already N1 is available, N2 we have to find. So for that, we have so many equations. Some are already available. In what way? This E2 is directly available as 4, because N6 is given as 4 moles. So N6, what is referring to? N6 is CO2 is given as 4 moles. So from that, I am getting this E2 as 4, and using that in this CH4 in the product, from which I am having 60 minus E1. Otherwise, I am getting this E1 also now solved. So E1 and E2 are available. Then what else is needed to get? We need to get N2, no? E1 and E2 are available, so you can get N2 directly. So N2 is nothing but the O2 moles of O2 entering the reactor. So otherwise, here we didn't worry about these reactions. Simply we return these moles. For to writing this, we should know only the stoichiometric coefficient with a proper sign, and the extent based on the first reaction and extent based on the second reaction. So the extent of 1 and 2 are somehow available, or is extent of 2 is available from the data of CO2, and using that I am substituting here and I am solving for E1. So E1 and E2 are now available. and N2 is simply available from this equation, substituting for the values of E1 and E2. So our problem is now essentially solved. So what is asked is we are supposed to enter the molar flow rate of O2 entering the reactor, which is simply 40. So this is the correct answer. Okay. Now we used to solve in this original approach. No, let us. Of course, this solution procedure already given in our LMS page, which is msubbu.academy. So here the reactions are already, of course, given. Given, right? Yeah, we are given with the reactions. So now, what are all available? 4 moles of CO2 and 4 moles of. So what is given is, we know this. What is it? CO2 and O2 and CH4 in the product. So based on the data of CO2, we can find how much of CH4 were utilized for that reaction. That is how much of CO2, so how much of CH4 undergoing this second reaction that is available. That is 4 mole of CO2 in the product indicates 4 mole of CH4 got reacted as per reaction 2, for which 8 moles of O2 is needed, got utilized. Okay, now how much of CH4 will be reacting as per reaction 1? That is equal to CH4 in feed minus CH4 reacted as per CH4 in feed minus CH4 used for second reaction minus CH4 in the product. You know, what is reacted is equal to what is entering and what is reacted for the second reaction and what is there in the product. So these are all simply by this how much of CH4 reacting as per reaction 1, whatever is CH4, whatever is entering in the feed minus CH4 in the product is simply CH4 as per reaction 1 and as per CH4 as per reaction 2. So that equation only written here. So we are given with the CH4 in feed, which is 60 mole per second, and CH4 in product also given, which is 26 moles per second, and CH4 used in reaction 2 is available from the data of CO2. From the data of CO2, the same amount of CH4 is utilized, same moles of CH4 is utilized. So we have the 4 moles of CH4 utilized. So now we could get to know how much of CH4 is reacting as per reaction 1. So there is 30 mole and CH4 according to reaction 2 is already available, which is 4 mole. Okay, now upon calculating this CH4, now what is needed is O2. How much of O2? O2 entering is equal to O2 used in reactions 1 and 2 plus O2 in the product. Now O2, whatever is entering is getting consumed and appearing in the product. So what O2 entering equal to O2 used for reactions 1 and 2 plus O2 in the product. O2 in the product is already given. O2, how much of O2 will be used for the reactions 1 and 2? That again depends on how much of CH4 undergoing reaction 1 and how much of CH4 undergoing reaction 2. So that is available. CH4 undergoing reaction 1 is given as 30 mole. So for 30 mole, we need 30 mole of O2. You check for this stoichiometrically balanced content, 2O, 2O. Okay, I think balanced. Second also balanced. So for this, we have 30 mole. And O2 for the second reaction, actually CH4 undergoing by second reaction is 4 moles of CH4 is undergoing according to the second reaction. So for 4 mole, we need 8 moles. So otherwise, the O2 entered equal to O2 used for 1 and 2, which is 30 plus 8, and O2 in the product, which is given as 2. So we could solve for O2 entering, which is the answer, which is 40 mole. Of course, this is also doable, but we should properly use our logic. This logic is again differing for persons. Whereas this approach, what is called as the extent of reaction, is very straightforward. Given the this product, so product will be what are the components possible in the product? So every component will be there in the product. In the case of incomplete reactions, so you write every component in the product. Then for every component, you write these moles using the initial moles and this extent of reactions. So these are all written for the components of this reaction mixture. And some data are directly giving this extent. Using that, we could solve for the other thing. So in that way, the first approach were kind of a systematic approach. Whereas here, we started from this moles of CO2 in the product. Using that only we could find that. What is the data given? The data given is 26 moles of CH4 is there, and 2 moles of O2 is there, and 4 moles of CO2 is there. We started from 4 moles of CO2. That is only found to be giving you the value of CH4 used for the second reaction. Then using this 26 again, we got the CH4 for the first reaction. So otherwise, there is kind of a risk which we don't know where to start. Somehow we have started, but that may not be the good approach for every problem. So whereas this extent of reaction is approach is though appearing to be slightly lengthy, uh, but the problem approach is straightforward. So now even there is one more approach, what is called as atomic balance approach. So that we'll now understand. So what is this approach? There is first, let us represent this. So we are given with this CH4, O2, CH4, HCHO, CO2, and H2O. And the molar amounts are given as 26 moles of CH4 and 2 moles of O2 and 4 moles of CO2. These are all the available data. And feed is 60 moles, 60 moles of methane. We need to calculate molar flow rate of O2, which is nothing but the N2, because we need to find N2. So now, how many atoms are there? What are the atoms are involved in this problem? So what are the atoms? So definitely C, H, and O. That is what is entering. And the product also have C, H, and O. So we can write the balance on C, H, and O. So three different balances we can write. Using that, we can solve. Let us see. First, write the balance for C. Service here, we don't write any equations. No stoichiometry here. Simply, we know the feed and the product molecules. So for that, some flow data are available. So using that, we are going to solve. So what is the atomic balance on C? So how much of atoms entering with 60 moles of CH4? 1 mole of CH4 is having 1 atom of C. Correct, no? There is simply 1 atom of C. So 60 mole of CH4 is entering. So 60 atoms of C is entering. This is the atoms of CH4, C entering. And where are C and leaving? C is leaving in CH4 and C in formaldehyde and C in CO2. So 26 moles of CH4 is leaving. 1 mole is having 1 atom of C. So 26 into 1. These are atoms of C in the product CH4. And in the CO2, we have CO2 is 4 moles of CO2 is leaving. For 1 mole of CO2, we have 1 atom of C. So it is 4 into 1. So this is simply molar flow, and this is how much of C is there in the molecule, in the component. So don't say like molecule. It's better to say like component. In CO2, one atom is there. So that's why 4 into 1, because 4 is the mole numbers and 1 is the this atoms of C in CO2. Likewise, C is also there in this formaldehyde. So formaldehyde molar flow we don't know, which is simply N5. N5 in 1 CH4 HCH4 we have 1. So in N5 HCH4 we'll be having N5 into 1. So this is the atom balance on C, from which we can solve for N5. What is N5? Otherwise we'll be getting the flow of HCHO, but still what is needed is the flow of O2. For that, okay, well, let us still have this value. This is atom balance on C is over. Now the atom balance on O you can write. So from O, how much of O is entering in terms of atom? It is 1 O2 is having 2 O, and N2 O2 is having N2 into 2. Or is this the O2 entering atoms of O2 entering, which is N2 times 2, and whereas this O2 leaving, N4 times 2, because one O2 is having 2O. So N4 O2 is coming, so N4 times 2O. So that's why this N4 times, of course, N4 is already available, which is 2. So that's why simply I'm having 2 into 2. And this HCHO, that is also having O. So otherwise N5 already available, which is 30. So 30 into O is the 30 into 1, no? 30 atoms of correct, no? 30 atoms of O is leaving along with HCHO, 30 moles of HCHO. So that is available. There is N5 into 1. And it is also leaving in the this CO2, which is 4 moles, and 1 mole is having 2O. So it will be having 8O. There is 4 into 2. Likewise, N7. What is N7? N7, this that of water. So one water is having 1O. So N7O. That is N7 into 1. So okay. Now this is ending up in terms of N2 and N7. So what is N2 and N7? That is we are getting a relation between N2 and N7. But what is still needed? We need to have only N2. So that is we have written balance on C and balance on O. And what other balance we can write? We can also write a balance on H. What is H? How much of H entering? This we have for 60 moles, we have 60 into 4 H atoms entering because of methane. So there is a entry. And what? How much of that is leaving? 26 into 4. And this is N5 into 2. Correct, no? N5 into 2. N5 into 2. Okay. Likewise, N7 into 2. Okay. So N7 already available as N7 only. N5 value is available as 30. So from that, at last, I could also get the value of N7. And using this in the equation 2, I can solve for N2. What is nothing but the flow rate of oxygen in the inlet. Otherwise, here, I don't consider anything about the reactions. So I haven't written anything reactions. Simply, I know this CH4 is entering, O2 is entering. I know these components are leaving the product. So this is the available data. I don't worry about the reactions and balancing the reactions. Simply from the data of this feed and from the data of product and feed and writing this atom balance on H, balance on the atoms available. It is simply balance on C, O, and H. Using these three balances, we could solve the unknowns. So this is kind of a nice approach for wherever you have a complicated reactions or sometimes even if there is no data about the reaction stoichiometry. In that case, we can very well go for atomic balance. Of course, you may be ending up with some many balance equations. Here in this case, we have only C, H, and O balance. Sometimes it may also have many other atoms also present. So in that case, you may be leading with many equations. But given the availability of a computer, you can easily solve any any number of equations, and the approach is very straightforward. Now here in this usual mole balance approach, we used to start properly. Otherwise, we'll be keep on searching for, we cannot arrive at this answer. Whereas this extent of reaction is also very straightforward. As like extent of reaction method, this atomic balance is also quite helpful. Okay, otherwise, sometime at least for this multiple reactions, this extent of reaction method and this atomic balance methods are quite helpful than the usual mole balance approach.